There are some things in electronics that are so fundamental that you just can't do anything without them. For example, capacitance, resistance, inductance. And there are some things that are almost equally as important that without them you could not do a lot of the interesting things we do. So without this particular phenomena, we couldn't have anything from the simplest radio to high-definition television to the remote that operates it to your cell phone. And many, many, many of our devices today, from analog radio to digital everything, would not operate without this phenomena. So what is that property that I'm so fascinated by? Well, it's resonance. And it's what you get when you have a capacitor and an inductor wired different ways to create either filtering or passing of signals at a certain frequency. And it's used in radio and television, in all sorts of digital devices. In fact, every digital device has one of these little things in it. They call it a clock chip, and all it does is it uses resonance to create a steady pulse of waves. The equipment I'm using today is this old signal generator I paid $5 at a Hamfest for. It's not wonderful. It's not like my old Tektronix, but does the job. It'll create some simple waveforms. And my recently acquired USB oscilloscope running on my laptop over here. All you need to create a resonant circuit is a capacitor, in this case a variable capacitor. This goes from 10 to 365 picofarads, and an inductor. This is a 100 microhenry inductor. I pulled out of something. And let me show you how I got these two and paired them, because I wanted them to resonate somewhere in the range of about 1 megahertz. So how did I determine that? Well, let me show you. Now you can download these apps from Play Store or whatever and run them on your phone or tablet. And this one will do find frequency. This is called Resonance Calculator, and I downloaded it from Play Store. This will find the frequency, it'll find the inductance, it'll find the capacitance, and you can set the different values over here, whatever you need. So you can say microfarad, picofarad, nanofarad, whatever. Like picofarad. Okay, and I picked a value that was in the middle of my variable capacitor, and a value for the microhenries inductor that I had. I had a 100 microhenry inductor, and it comes out about 1.17 megahertz. And when you hook that up, let me show you what happens. You can see I've got my capacitor set, so it's about halfway, and I've got this set at about 1 megahertz. So how do I know that that's the fundamental frequency, that that's the harmonic frequency of this circuit? Okay, well, I'm going to move this knob, and if this is correct, if I'm at the resonant frequency, then what will happen is the waves are going to shift this way as I change the frequency, and that's okay because we know that this is changing the frequency. But at the resonant frequency, what will happen is the waveform, the height vertically, will be at the maximum. If I go above it, the wave will shrink down this way, and if I go below it, it will shrink down this way. So that's how I know. So let's take a look at this. Going up, starts to shrink down, and as I go back, it maxes out about 1 megahertz, and as I get past 1 megahertz, it goes back down again. It starts to shrink vertically. So that's how we know we're at the resonant frequency of that circuit. Well, let's make a change and verify this. Let's set the capacitor at a different value and see, in fact, if we get a different resonant frequency. As you can see, I've changed the capacitance to be higher capacitance. I've rotated more plates into the circuit, higher capacitance. And that should mean a lower resonant frequency. Now I've got this set to 700 kilohertz right now, which is 200 kilohertz lower. Let me see if I can prove to you over here that, in fact, this is the most efficient point, i.e. this is resonant frequency for this circuit. Now remember, we don't care about the change this way. This is just change of frequency, and we know we're changing the frequency. We're doing that on purpose. What we're looking for is the vertical change this direction that tells us how efficient the circuit is. Okay, let's take a look at that. As I rotate higher frequency, go to a higher frequency, it should start shrinking. Went up a little bit. I didn't have it set exactly, so it starts shrinking as I go higher. And as I go back towards 700 kilohertz, it maxes out and then it will start to shrink again. So that tells me that I'm at around 700 kilohertz, a little bit above 700 kilohertz. The circuit is the most efficient. It's resonant. And that's what resonance is all about. Well, resonance is used in every complex circuit, and that's really an interesting fact. But what's a practical thing you can do with it? Well, so for example, let's say you wanted to know the value of this inductor, but it's not written on there. Well, you can substitute a capacitor of a known value, like this one, into this circuit, and by knowing the capacitance and the frequency that it resonates at, I can calculate, using that app we saw earlier, calculate the value of the inductor. And vice versa. If I have a known inductor and I want to know, for example, where this capacitor is set, what's the capacitance of this, where it's set right now, I can do that too. I can calculate that too. So it has a lot of practical applications, and frankly, it's just fun to play with. Okay, well, that was it for today. I hope you found it useful and interesting.